Here we have a question about trusses. The question is given in a format of multiple choice, and there are 4 possible answers in the 4 corners of this page, as you can see. The question is this: members in the following pin-jointed truss will experience tension, compression, or zero force. Choose the solution that matches the loading given. If you'd like to give this a try first, please pause the video now and then unpause it when you're ready. When trying to find zero force members, which is the first thing we should do, there are basically 3 things that we need to look out for. Firstly, we're looking for 2 members that arrive at a straight line or collinear to each other. This could be in this kind of form or in any kind of shape like this. Oops. Don't forget all of these are pins. Through vertical and horizontal equilibrium, these 2 forces in the truss members must be the same. If there's any difference in any of them, there will be an acceleration on the pin joint. Therefore, with that knowledge, if we have a third member coming in, such as that, that must mean that the third member must have zero force, because of the fact that if there is any force on it, then that would cause the pin to accelerate in the direction of the force. So that's condition number 1. We're looking for a member that butts into 2 members that are already collinear. Secondly, we need to look for 2 members, precisely 2 members, that come into each other at an angle where that angle is not equal to 180 degrees. Let me just draw a dotted line here. Because whatever force we put on it, if you try to resolve it horizontally, for instance, well, then there is no vertical equilibrium. If you try to resolve it vertically, well, then there's no horizontal equilibrium. The only possible way that these 2 trusses can be in equilibrium is if they are zero force. So with that knowledge, with these 2 conditions, let's try and solve this. The first thing that jumps out at me is this member here. You see, we have a member that butts into an already collinear pair of members. Therefore, I already know that this one will be a zero force truss member. Bear in mind that these conditions that I mentioned only apply where you have nodes where there is no external force or a reaction force acting upon it. It's important to have that in mind because, for instance, this top node here does have an external force acting on it, and therefore this would experience some kind of compression force. So with that in mind, then, we already know that this is a zero force member. Can we eliminate some of these? Well, yes. This one says this is tension, so already I can say that won't be it. That's a 0. That's a 0, and that's a 0. So we've got B, C, and D. Okay. What other clues can we have? Well, the other thing that jumps out at me is an imbalance of forces here. We can't have a 0 and a tension when there are only two members to counteract each other's forces there. So already I can already say no to that one as well. Similarly here, one says compression, one says tension. That would imply compression and tension like that. But you see, at this node here, we get an acceleration to the right because there is no balance at that node, even though it's vertically in equilibrium, but horizontally it is not. So we can say no to that. And actually, we don't need to solve the rest. We already have our answer by process of elimination. C is our correct answer. Here we have a new truss. Here the supports are a roller at one side, which means this can only take vertical reaction. There cannot be a horizontal reaction. And because there are no horizontal applied forces anywhere on this structure, that means the one on the left is only taking vertical as well. This is a symmetrical structure. So now let's try and identify our zero force members then. We're looking for collinear members and then one member jutting out from that. Can you see one? The answer is right here. If we look at this node, there is no applied force there, so we can look at this one in isolation. And we have two collinear members there and one member coming out here. So whatever forces are in that, they have to be in equilibrium, and this one has to be the one that is a zero force. So I'm going to blot that one out right now. And actually, that is all we can say for the zero force members. Oh, is it? No, it's not. My mistake. Let's take a look at this joint here. We know that there cannot be any horizontal force because of the fact that this is a roller. And so to maintain horizontal equilibrium here, because this one is a vertical member that cannot take any horizontal, that cannot cause any horizontal load on this node. So this one has to be zero as well. Similarly on this side, even though this support can take horizontal load, there is actually no horizontal reaction here. And so that means that this whole thing has to be in equilibrium. And that member there is taking no load. Let's take a look, and from what I can tell, there are no more zero load members. Admittedly, this does look quite precarious because it looks like it's just standing on stilts, but obviously this is an idealized situation. But here, we know then we can start resolving our forces. Oh, sorry, that's too broad. No, that's probably okay. That has to be a compression load due to the fact that this joint needs to resolve vertically. Because this joint here needs to resolve vertically, we know that this is a tension load as well. And because we now have a force to the right due to that, we now have to resolve a force going to the left due to that. Because we have a vertical force, vertical component of this here going up, this vertical force must go down. Don't forget, we're just looking at this joint in isolation. It's not entirely obvious here because of that force, but we know that that this whole member is in compression. And now because that is going to this has a horizontal component going to the left, we know that this has to be in tension as well. And what else can we say? Well, this force is being applied downwards, so we know that this has to go upwards. These two members have to sum up to cause a reaction, so a force to go upwards to counteract that. So what I'll do, actually I will draw the left hand side first. And what I'm going to describe now is actually something that's, well actually before I do, I need to resolve this member here. We've got two forces with components to the right and nothing to the left, so we know that this has to go to the left here. Okay, back to my original point. What I'm going to mention now is something that we use a lot in engineering in general, but also science, okay, is that this structure is symmetrical. And because of the fact that it's symmetrical, because the forces are the same both sides, we can actually just mirror this entire, all the member forces in their entirety here. Like this. You may think, well, how can I justify that? But that itself is a justification. If the structure is symmetrical, then these member forces have to balance out. Otherwise, you cannot have internal forces that don't balance each other out. Otherwise, the structure would spin by itself. So no, this is a perfect justification, and these are our forces. We've got compression, compression, and actually we have compression all along the top and tension along the bottom, tension in these two diagonals, 4 diagonals in fact, and compression here. And finally, if I just scrub out my original markings of these, oops, these are zero force members, and this is our solution. Let's take this truss. Here we have an uneven loading. So first things that we need to look out for then, let's draw in our reaction forces. Well, these are going to be vertical loads. They won't be the same because it's an asymmetrical structure, but these two are still going to be vertical nonetheless. Let's do our usual trick of trying to look for the zero force members. We're looking for collinear members and a third one jutting out of it. Can you see it? Right here at this node. These two members are collinear, and we have a third one here. So we know that this member has to be this member here has to be a zero force member. But look, because we've identified that original force to be zero force, then now we have another situation here. We've got two collinear and a third one jutting out. So in fact, this also has to be a zero force member. Is that it? Yes, I think it is. So now we have to start resolving the forces. We have a vertical component here at this node going up, so we have to balance that with a vertical component going down. And now because we have a component going to the right, we have to have a component to balance that to go to the left. We now have a component, oh, actually let's do this side here. We have a force going up, so this force has to go down. And similarly, we've got force going to the left here, so we have to balance that with a force going to the right. Now let's look at this load. Well, if we look at the horizontal force only, we've got this force going to the left, so that has to go to the left as well. This force is having an external force pulling it down, so that means that this member has to be in tension to balance that force there. we know that these two members here, they have to be in equilibrium to each other, such that in the vertical equilibrium. If one is in tension, the other is in compression. It's not entirely obvious what it is yet, but let's take a look at this node here. This vertical member will not be able to stabilize that joint in the horizontal direction, and we've got a left-hand component from this force, so we have to have that balancing out like that. And now, because we have two vertical upwards components, this member here has to balance that node there downwards. And now, because we've identified this one to have a vertical upwards component for this node, this one has to have a vertical downwards component. And this is our full solution: compression, compression, compression. So compression on the two chords around the top sides, and these are all tension along the bottom. And this is a tension for the king post. Here we have a tension there, and we've got compression there. Let's restore our original members here. And these are our zero force nodes. And that is our full solution. Here's another truss. Let's do our usual and try to identify the zero force members. So remember, we are looking for two collinear nodes and a third one jutting out, or two members that are not 180 degrees to each other. Two members that are not collinear to each other. Can you see it? The answer is right here and right here at first sight. So let's look at this one. Basically, whatever horizontal force that this member puts would cause this joint to be in to not be in horizontal equilibrium, and this vertical force, whatever force is applied, must cause this to not be in vertical equilibrium. So in fact, these two are going to cancel. These two are going to be zero force members. And with this one here, well, that central pillar, that central member, has to be zero as well, because whatever is applied there will cause that top center to not be in vertical equilibrium. Let's draw in the reaction forces. Well, this is a roller support, so it can only possibly take a vertical load there. And because we do have a horizontal applied load here, then this has to be a horizontal reaction, but because we also want vertical equilibrium due to this reaction here, this will have to be vertical equilibrium there. Right, so now we can solve for the rest of the structure, because for the rest we do not see two members that are collinear with a third one jutting out and not have any external or reaction forces on it. And we don't see any any single node with only two members that are not collinear to each other. Right, so now we can resolve this. Let's take a look at this joint here. Well, there's a horizontal force going to the right, so we need to balance that with a horizontal force going to the left. And what about this member? Well, we know that there's a vertical force here, but we do have an extra member here that could take vertical load. So we're going to need to be careful about this one here. It's not entirely obvious, but actually yes it is. What am I talking about? It has to be a zero force because of the fact that there's no vertical component here. So actually let's draw this one to be blank. Okay. Now this one is very obvious. We've got vertical force going down, and so this one, the vertical component has to go up. And then let's see, we've got some force going to the right here and also force to the left. So this is not entirely obvious what it needs to be, but intuitively you would say that, well, if a structure is pushing it to the right, and well, actually, yeah, let's resolve it going backwards from here. Okay, intuitively anyway, that feels like that should be in tension, because if that's pushing it, well, I mean, something has to pull it back onto this one here, because that's the only thing that can take a horizontal reaction. But let's work from the back. Here we have a vertical load going up, so we need to have it react, the member pushing it back down here. And because of that pointing to the, have a component to the right, we need to have this member having a component to the left. We've got a component going up here, going up, so this one has to have a component going down, because that's, these two now have components to the left. This top one has to have a component going to the right. That's in compression. And because these two are collinear, these have to be the same as each other. And now what? We have force going up and to the right, so this has to go down for vertical equilibrium there. And now look, we've got all three forces pointing to the right, so I was right there that force there has to be tension to pull it back in. And that's actually all of our members: compression, 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 another one, and another one, compression here. These are in tension, and if I bring back the original members, these are zero force members. Sorry, one more. That is our full answer.